Okay, so in the last class we have been talking about the excluded volume interactions, that is, just to remind you very quickly, is when the interactions vary with the physical distance, not the distance along the contour. So, we are looking at let us say two segments which are far along the contour, m minus n is much higher than 1, but they are close together, and I already pointed out that ultimately what matters is the interactions between the segments at this distance should be comparable to or higher than the thermal energy. If it is smaller, then we do not care about it. So, if I call this R, then whatever interaction we will define, we want it to be higher than the thermal energy of the system. Okay. So, in this class I will take this further. The first idea I want to introduce is why do we call these interactions an excluded volume interaction, and then we will do a small explanation of first what types it can be. We already said it can be attractive or repulsive, but we will take it slightly further, and then finally we will derive what is known as a virial expansion starting from this particular point. Okay. So, the first thing is I want to give it a particular expression for the interaction, and I can choose any particular energy scale, right. It does not really matter if I divide this by kBT or anything. So, I can start with a scale, and let us say I am defining in this particular way. So, I have chosen kBT as a scale, and then since we have taken kBT, kBT already has units of energy. So, whatever else we have is some dimensionless parameter that we do not know, but it depends on the distance. So, it is a dimensionless function, to be more precise. Okay. So, now if the attractions are repulsive, then what essentially it means is this number v tilde has to be higher than 0. If the attractions are attractive, this number should be less than 0. Other way to say it, like if they are attractive, they want to come together, that is give rise to the lowering of energy. If they are repulsive, if they come together, that give rise to an increase in energy. So, depending on that, we are assigning a sign to the v tilde. So, if I define in this particular way, let us say this is my R, where R is equal to R m minus R n, and I am doing versus say the absolute value of the R. So, let us say I also do it here. I assume that it only depends on the distance. We can talk about specifics later, but most interactions only depend on the distance, not the distance vector, like Coulomb interaction only depends on the distance. So, now if it is higher than 0, we can say it is repulsive, and if it is less than 0, we can say it is attractive. And then how fast or slow the interaction depends on R defines what is known as a long range interaction or a short range interaction. For example, the Coulomb interaction between like charges is repulsive and it decays like 1 by R, where R is this. The actual formula, just to recall, also contains some constants and the charges, but we are looking at how does the interaction scale with R. Okay. Similarly, if it is attractive, it is like this, it is like plus minus or minus plus, essentially the same thing. This also decays like 1 over R. Now, 1 over R is of course not a very rapid decay. If it goes, if you double the distance, the interaction is halved. If you make it 4 times, the interaction is like 1 by 4. We know about functions that decay faster than this, like exponential of something, they decay much faster than compared to 1 by R. Of course, if I take of higher powers of R, 1 by R to the power square, that will decay faster compared to 1 by R, because if I say double the distance, the interaction now will be 1/4 as opposed to 1 by 2 in the case of 1 by R. Okay. So, there is something known as the Wonderwall interaction that is present even between neutral molecules, and they are known to decay by 1 by R to the power 6th. That really means a very rapid decay. Now, they can also in principle be both attractive and repulsive, but mostly we talk about attractive van der Waal. And they are like, so now if you think about it, since we have said already that the interactions must be higher than kBt for them to have any effect. So, what it means in turn is, let us say after certain distance, this interaction u becomes less than kBt, then after this distance we should not worry about that interaction. That essentially means is this is a short range interaction, because after a particular point the energies will become smaller than kBt, and this will happen much earlier in this case than compared to the Coulomb interaction. So, for Coulomb we can call it as a long ranged interaction. Okay. This is again to write here is Wonderwalls by the name of a scientist. And this you can also think of as a Wonderwall, but typically we talk about Wonderwall interactions only. And this is my Coulomb, and this is also my Coulomb. Just keep in mind that we also have talked about short range and long range interactions in the context of the ideal chain models, but though that time the range referred to the distance along the contour, not the physical distance. So, now and after this point, when we say a short range and long range, we are referring to the actual physical distance, not the distance along the contour. Okay. So, now if you really think of the short range interaction case, that is really falling off very sharply in the limit of like very rapid decay, we can really approximate this as like a delta function, right. What essentially delta function is in this case is is right here in the case of repulsive interaction, because anyway for r equal to 0 it is very high. That means as soon as the polymer chains or segments cross, we have a very high interaction, and then otherwise it is 0, because anyway after some distance it is going to fall off and the decay is very rapid. The decay is anyway very rapid compared to say a long range interaction. So, we can approximate using a delta function. Okay. The same idea we can apply at the bottom. We can call this a delta function, and then in reality it was something that was rapidly decaying, but now we have approximated as a delta function. Okay. Now, what essentially it means is only when the chains cross, we will only these guys we will consider for the purpose of excluded volume. If it is not crossing, that means we will not consider it. Okay. Now, before we proceed from here, just keep in mind that when the chains cross, it is we are not making any kind of a physical error in terms of stating this. It is not like two atoms are sitting on each other. As we have discussed earlier, what it really means is two segments of the polymer chain has come together. Now, individually both these segments are in different conformation. So, we do not have a one-to-one overlap of atoms, we have an overlap of different conformations, and essentially the kind of picture we will have at the level of molecule will be this is my one conformation and this is my other conformation, as opposed to having directly both the carbons at the same place. So, this is not really happening. What we have is like this, because the segments represent different conformation. That is one point to make here. The other point to make here is how much do we care, because we are doing a very toy-like model. We care about scaling laws. We know that at molecular level these models will not really work. Their resolution is not to the level of atoms, but they still give you a good scaling law. So, we have to live with these kind of assumptions, but the assumptions are not very serious. That is what I want to make. Okay. So, as I have already said, this V can be approximated to be a delta function where this function is essentially not equal to 0 for R m is equal to R n and is equal to 0 otherwise. This is how we typically think about it, but to be mathematically rigorous, what we really mean is if I integrate this function R over the entire space, that really means in 3 dimensions the function in x, y, z, dx, dy, dz, then this must be equal to 1. This is what is meant here, that the integration of the delta function is equal to 1 over the entire space. So, since this has a unit of volume, this has a unit of 1 by volume, because 1 is dimensionless. So, this entire thing delta has a unit of 1 by volume. it must be multiplied with something of having the unit volume, because we know V tilde is dimensionless. Okay. So, for the same reason we multiply with a parameter V which has a unit of volume. Okay. So, just to explain the point again, because it is very important. First we write the V tilde that we got or we started with in the expression of the interaction energy. First we say that the interactions are short ranged. This assumption will not work for Coulomb interactions, for example, but they will work for Wonderwall's interaction. First we assume it can be approximated by a delta function. Then we said that the delta function in 3-dimensional space will have a unit of 1 by volume, but V tilde should have a dimensionless units, it must be dimensionless. So, we must have to multiply the delta function with something that has a unit of volume, and we call that particular quantity V as our excluded volume. So, in some sense you can think of it physically as some volume around the segment where the interactions become effective between the segments. Means we can think of, like, let us say if I start at segment M and I go to a small distance, I will see some Wonderwall that is higher than kBt. If I go to longer distances, the interaction is present, but that is smaller than kBt. So, we can think of a smaller volume around the segment M for which the interactions are substantial. That particular volume we can think of as the excluded volume, but the analogy ends here because it is not always excluded. The parameter V, as we will see, can be both positive and negative, because V tilde can of course be both attractive and repulsive. Okay. So, for V higher than 0, that is for the excluded volume parameter, we call the system in the good solvent regime, because that is when we have repulsive interactions, and for V less than 0 we call it a bad or poor solvent. Now, it is anybody's guess of what we can do for the case of ideal chain. It is not good nor bad. So, it has to be something like V equal to 0, and that is what we call as theta solvent or theta conditions. Okay. So, now from now forth we will talk in terms of the parameter V that has a unit of volume, and we will see what will happen for positive V, negative V, 0 V and so on. And just keep in mind that this has a unit of volume because the delta function had a unit of 1 by volume. It refers to some sort of a volume around every segment which are somewhat excluded in the sense that the interactions are effective there, but then the interactions can be both positive and negative, and so it is not that the polymer molecules cannot come there, the segments cannot come there and so on. So, now that was between one pair of segments M and N. Okay. So, now if I look at the total interaction energy that is present in the chain by virtue of this excluded volume interaction, then we must have to integrate the energy we have got between M and N for basically the index going from 0 to capital M, that is the number of segments, because that will look at all possible pairs of segment in the system. Okay. So, the total interaction energy will be equal to I have defined two dummy variables N and M, both are going from 0 to M, that is along the contour, and then we had a delta V assumed to be a constant is moved outside the integration, and we have a factor of 2 because if I am doing an integration twice from 0 to M, we are looking at basically every pair twice. So, it will, let us say M and N will come twice, one as Mn, next time as Nm. So, that is why we divide by 2 in the integration. Okay. So, now we can also define something known as the local concentration of segments, and the quantity is defined as C of R as a delta function of R minus Rn summed over all the segment. What essentially it means is, if I look at any particular point in space and let us say it is R, then the number of segments passing through this particular point will be a sum over all the delta functions, where I basically iterate over every segment and see whether it is at R or not. Okay. So, let us say for example, if I look at this point here, in this case 2 segments are passing through this point. So, the function should have a weight of 2. At this point we should have 2, at this point it should be 3 because 3 polymer chains come here, everywhere else it has to be 1, right, and here it is 2, 2, 2. Okay. So, if more segments are passing through a point, we say the concentration there is higher. Here we think of concentration as the number per unit volume. Every time we count, we increase the number, and delta function already has a unit of 1 by volume. That is how we get the concentration. Okay. So, now again in discrete space, this can be 0 to, again I am sorry, again when we replace the summation by the integration over the contour that we can do for large M, this is so now I am going to use an identity here that will really make things more convenient from now, and the identity is for the delta function. So, we can write this particular term as dr delta of R minus Rn delta of R minus Rm. Of course, there is a mathematical proof for this, but it is not very simple to see. It's always very simple to see like why it should be the case. So, Rn has to be equal to Rm, and that must be equal to some R. So, if I integrate over all possible values of R, the product of these two, that R equal to Rn and R equal to Rm delta functions, then if I take a product, it basically corresponds to Rn is equal to Rm, and since we integrate over the entire space, this captures all the possible values of this position. Okay. So, now if I use this particular relation here, so now if I see here, I can move the integration with R outside, something that we have been doing. We have been interchanging the signs of integration, keeping in mind that basically we want to figure out which order is more convenient for us. So, in this case, we will have kBt and then we have a dr, and then you can see there are two integrations here, one with n and one with m, but the delta functions now, once they are separated, one of them is in terms of n, other one in terms of m. So, I can really write it as two integrations . So, now you can identify, since we have defined the concentrations, the local concentration already, this is my C of R and this is again my C of R. So, I get the same function twice, and what I do get is kBt V by 2 dr Cr square. Okay. So, that really means that the interaction energy that we have got goes like the squares of the concentration. What I will do in the next lecture is to say that we have made an assumption here that there is only a 2-body interaction. In reality, we can have a 3-body interaction or a 4-body interaction, and what this amount to is what is known as the virial equation that we will derive, and based on that we can then do the Flory theory and derive the scaling laws for the good solvent case and the bad solvent case. Okay. So, we will stop here. Thank you.